So recall the job we have, the problem we have is that we have n jobs, each having a weight and a length, and we want to find an ordering of these n jobs, which is essentially scheduling, which minimizes what we defined as the weighted completion time. Okay, so now the brute force algorithm, naive algorithm, was uh, too expensive, order of n factorial. So we're trying to find a better way. Okay. In particular, we are trying our greedy strategy. Okay, is there some greedy way of solving the problem? Okay, so one common way to approach a given problem, any given problem, which you probably already naturally do, is to try and solve the problem for simple cases. Okay, maybe some special cases. We try and solve the problem and then see if that gives us some clues, some hints of how we could solve it for the general case. Okay, so some simple cases. What could some simple cases be in this case? Let's say like a special case. Let's say a special case one. Let's say all the jobs have the same length. Okay, we are all of the same length, but different weights. Okay. So let's say this happens. This is the scenario. Okay. So what could we do in this case? Okay, we all have the jobs have the same length. Right? They all have the same length. Okay. So what do you notice about this? What happens if we permute these jobs, right? If we move these jobs around, will the completion times, the overall completion times, will that change? Okay. And what about the weighted completion time? Right? If we want to minimize these weighted completion times, what would we need to do? Right? So maybe take an example here. So maybe let's go really simple and just consider these two intervals. And so they have the same length. Let's say they have weights. I'll denote the weights in this. So as weight 1 and this as weight 2. Okay, and let's draw the other scheduling here, where again they have the same lengths, but now the job with weight 2 is scheduled first and the job with weight 1 is scheduled later. Okay, what happens to the weighted completion time? Right. For this, first scheduling, the weighted completion time is 1 times whatever the duration of the job is, right? Let's say L, and plus the weight of the second job 2 times the second job will get completed over here. It will get completed at time 2 times L, right? So this is 5L, right? Where L is the length of the job. And over here, the weighted completion time for this scheduling will be the weight of the job 2 times its completion time is L, plus the weight of the next job 1 times its completion time again is 2L, right? This job, this is getting completed at time L over here, and this is getting completed at time 2L. Okay, so how much does this work out to? Well, this is just 4L. Okay, so you see that, and you might have also intuited that putting the higher weight jobs earlier, right, will lower the weighted completion time in this case. Okay, so you can extend this to any number of jobs, and you will actually see that in fact, if the jobs have the same length, then you could simply arrange them in decreasing, right, in decreasing priorities, in non-increasing priorities, right, and you just schedule them in that order, and that would give you the lowest weighted completion time. Okay, so yeah, so what we're saying is, if the lengths are the same, then we want to pick an order where the higher priority jobs are scheduled first. Okay, so that's one special case. What about, let's look at this other possibility. We'll say all jobs have the same weight. Okay. Okay, they have the same weights, but they have different lengths. Okay, so they are all of the same priority, right? Everyone is equal in terms of priority, but they all have different durations. So in this case, how do we schedule? So let's say we have something like this. We have two jobs which have these durations. So let's say the first one has duration, this has duration 1, this has duration, let's say 3. Okay? And the other scheduling is, you first put the job with the longer duration, and then you schedule the job with the smaller duration. Okay. So what happens to the weighted completion time in this case? In this first case, the weighted completion time is the weight W times the time the first job completes, that is simply 1, plus the weight of the second job, which is again W, because they all have the same weight, plus W times the time at which the second job completes, which is 4. Okay. And for the second possible ordering, in this case, the weighted completion time is W times the time at which this job completes, which is 3, plus W times the time at which this job completes, which is 4. Okay. So here we have 7W. Okay. So what we observe is that when we have the jobs having the same weight, we would maybe want to schedule the smaller duration jobs first, right? And keep the longer jobs later. Okay, because a long job initially would increase the completion time of all the subsequent jobs, right? Which would increase the weighted completion time. Okay, so these are giving us some hints of how to order the jobs. Okay, so now for the general case, right? So if you look at our general case, for the general case, let's say for jobs I and j, if we're seeing that if the weight of job I is greater than the weight of job j, okay, and maybe the length of job I is less than the length of job j, okay, then our intuition is basically telling us we schedule job I before job J, right? So trying to generalize now from our special cases. We said the lower duration job should come first, right? So this is happening here, or we are saying the higher priority job should come first. If the weight of I is greater, then you schedule I before. Okay, so this is fine. This looks good, but of course, this can happen, right? What if we have weight of I being greater than weight of J and the length of I also being greater than length of J? Okay, or the other possibility, Wi is less than Wj and Li is less than Lj. Okay, what happens in these scenarios? What do we do here? Okay, because if we are looking purely at this, Wi is greater than Wj, this would, our intuition would suggest to schedule job I before job J. And if you look at purely this would suggest schedule job J before job I, right? So there are two conflicting results that um, how can we kind of decide which job to put first in this case? Okay, we have these two parameters, the weight and the length, that are suggesting different schedulings. Okay, so the idea here is, the attempt here is, can we somehow combine these two parameters into one single parameter? Okay, so we'd like to fuse them into a single value, which we will call a score. Okay, and once we compute the score, so what we'll do is for each job, we'll somehow fuse these weights and lengths into a single value, a score, and then we will simply say the job which has a higher score will be scheduled before a job which has a lower score. So our idea here is to compute a score for each job using these parameters W and L, and okay, then our greedy algorithm will simply schedule the jobs with the higher scores before a job with the lower score. Okay, so it will simply sort the jobs based on their scores, and that sorted order would be the optimal way to schedule the jobs. Okay, so I'm not even writing this greedy algorithm. It's so simple. It'll just sort the jobs based on their scores and then schedule them in that order. Okay, so, well, that's all well and good, but how do we actually compute the score? Okay, and why will it actually be optimal, right? There are, of course, many unanswered questions. Okay, so a score has to somehow fuse these values, W and L, together into one value. Okay, so there may be different candidates for a score, right? So a score, maybe let's give it a name, score SI of job I, right? So one way to define this is maybe Wi minus Li. Okay. So why are we doing this? Well, what we would want is, as the priority increases, the score should increase, right? We want that the higher priority jobs get a higher score. We want them to be scheduled earlier. And it was the opposite for the length, right? We wanted the jobs which had a higher length to be scheduled later, right? So a larger length should get a lower score. And that's why we have this minus Li here. Okay, so this would ensure that. Okay. So this is one possibility. Another possibility is we define the score as the ratio of the weight to the length of the job. Okay. So over here again, we see that as WI increases, the priority increases, the score is also going to increase. And as the length increases, the score is going to decrease, right? That's what we want. We want the lower length jobs to give a higher score. Okay. So these two are possible candidates. And you could imagine there are infinitely different ways of defining scores, right? Which will give us this behavior, right? I could maybe simply say this whole squared, right? That would also give us a score. Okay, so what value of score should we pick? Which one really works? Okay. So it turns out that the one that works for us is this particular definition of the score. Okay, this one, though it seems interesting, it doesn't really work. So I leave that as an exercise for you to figure out a counter example. Okay, figure assignment of lengths and weights for which this particular definition of a score will not give you an optimal solution. Okay, I highly encourage you to do this. Okay, so what we are saying is that now our greedy algorithm will use this definition of a score. So what does that mean? If I have the n jobs with these different n weights and lengths, I'll simply, for each job, I'll compute the score. And then next step, I will sort all those jobs based on the scores and schedule them in that order. Okay, so the greedy algorithm is clear. Each job, compute the score based on this, sort them in non-increasing order or decreasing order, and schedule the jobs in that order. Okay. So if you have n jobs, you see that the runtime of this algorithm was simply order of n log n, right? It's basically the sorting that is going to take the most, right? I'll spend linear time order of n time to compute the n scores, and then I'll spend n log n to sort them. Okay, once I've sorted them, that's it. That's the order that I'm looking for. Okay, so why is this actually correct? Okay, why is this particular greedy algorithm, why is it that the scheduling it returns is the best possible scheduling? Okay, that is, why is it this? It gives you the scheduling which has the least possible weighted completion time. Okay, that's what we need to understand.